check this out. We've got something really fun today. This is so amazing, man. Oh man, again?
Let's warm up by looking at sigma notation. It's a convenient notation for adding or summing many terms that can be expressed using a common formula. This symbol sigma is a capital Greek letter, stands for summations. The index will start at the first value here, and it will be put into the common formula, and then the index moves up by 1, and each time that value is put into the common formula until we get to the last value getting put into the common formula, and then all of them are summed up. So the first term here would be f at 1, because this one says that's our starting value. And then we would add f at 2, we would add f at 3, and we'd keep adding until we got to f at n, or our last value there. Let's try these numerical examples. We've got k squared is our common formula, and k starts at 1, goes to 5. So our first term would be 1 squared, then 2 squared, 3 squared, 4 squared, and last 5 squared. So again, the index moves up by 1 until it reaches the last term here. And then we can just add these together. So 1 plus 4 plus 9 plus 16 plus 25. Looks like that will be 55. Let's try the next one. It's got a little bit more of a complicated formula. So I start off with 1, which is a common place to start, but it doesn't always start at 1. And there is my common formula evaluated at 1. I'm going to add this common formula evaluated at 2. So 2 times 2 squared minus 2. And then plus my last value here is 3. So 2 times 3 squared minus 3. I just need to add all that up. So 2 times 1 squared is just 2. 2 times 2 times 2 is 8. And 2 times 9 is 18. And 2's cancel here and here. We got a 26 minus 4 is 22. 11.1 and 11.2, the definite and the indefinite integral. To find the area under a curve, we can create and add up a certain number of rectangles that fit under the curve in some consistent manner. So in the first example here, I've got the top right corner matching up with the function. And I made 6 of them in between -3 and 3. In this one here, I matched up the top left corner. And you can see that some of these bars will overestimate the area and some will underestimate the area. We could create rectangles where the middle touches the function, and then on the same bar, some of it theoretically would be over and some of it would be under. That'd be a good way to get some more accuracy and less bias. Or we could, if we wanted to find an upper and lower bound, we could create our rectangles so that they were either always above every time or even always below. Now, adding up a bunch of rectangles is usually a lot more work than just taking the integral if we can find the antiderivative, and is only an estimate anyways. So we'd like to integrate if possible. If we make rectangles infinitely thin and then sum up infinitely many of them, we're going to get the area underneath a curve. And we write this in sigma notation. We're saying that we're going to add up all of the rectangles. So this would be the height of the rectangle, and this would be the width So we're finding the area underneath the curve from A to B, and we're cutting it into n pieces. So that's what this equation here says. The difference between A and B, and divide by n gives us our width, or our delta x. The height, in this example here, we're lining the top corner of the rectangle up with the function. So the height is just starting at A. We're going to add any I number of delta x's to get here, and then we're going to evaluate the function at that point to get the height. Okay, then we're going to add up however many there are, and we want to find the actual area under the curve, so we're going to let our n approach infinity. And that's what the integral is. It equals this limit. So what is this integral? There are two types of integrals that we'll be looking at. The definite integral. And it's called the definite integral because it's definitely in between a and b. So it's got some upper and lower bound here. And we've done something like this before with area under a curve. It's just the antiderivative evaluated at the upper bound minus the antiderivative evaluated at the lower bound. So that's how we found the area under a curve before. And we have this, the indefinite integral, which means there's no upper or lower bound here. So it's just the most general antiderivative. So from now on, we'll most likely be writing them like this and this, as opposed to using this notation. This long elongated s here is the integral sign. It was introduced by Leibniz, and it's s for sums. So the procedure of calculating an integral is called integration, and it doesn't always represent an area, and we've kind of seen that before. If I'm not paying attention and I just do this with my antiderivatives, I can get negative area and zero area and things that don't make sense in terms of area. Here's the pieces of our integral. So we have the limits of integration. There's our upper limit. Remember, it's the one on top. There's the lower limit. It should be a smaller number. There's our integrand. And this dx is part of the integral. So you can think of it as the end of the integral. Okay, so it tells us we're integrating all of this stuff and stops here. And this also tells us what variable we're integrating over. So once we start doing double integrals, and we'll have the dx and say dy going on here, this will tell us which one we're doing first, or which integral is inside. Now this also could be thought of as delta x from the last slide, an infinitely small piece, but some people don't like that definition. You also have to watch out because dx is used differently in different circumstances. And we're almost done the course, and we finally get to the fundamental theorem of calculus. And that would be if f of x is continuous on the interval a to b, then the integral from a to b of f of x is the antiderivative at b minus the antiderivative at a, where f is any antiderivative of f of x. Let's analyze this fundamental theorem of calculus. Got a few questions. Why does f of x need to be continuous on the interval? Continuous means there wouldn't be any breaks or vertical asymptotes. Well, we can't find area under nothing. So if my graph here had a break, and then I'll exaggerate this hole here, just start it over here, and I'm trying to find area, and then what? So I can't do that. Integration won't work if there's a hole in my graph. There's some kind of discontinuity. And why will any antiderivative work? Well, we talked about that before, And that would be because the c value will just cancel out and we don't care what it is. There are some properties of integration that you probably want to be aware of. If you have a constant here in the integrand, you can just take it outside if that helps simplify this. And if you are integrating the sum or difference of two functions, you can just work with them separately if that helps. Or if you had two of them separate and they had the same limits, then you could put them back together if that would help. Let's look at these examples here. We've got the antiderivative of 1 over x squared, so that would be negative 1 over x. And we're doing an indefinite integral here, so we put a plus c here. And this is just the most general antiderivative. Let's try this one here. We've got 1 over the square root of x, and that would be the square root of x, or x to the power of 1/2 if you prefer. When I take the derivative of this, I'm going to get a 1 over 2 here, but I don't see any of that. So I'm going to put a 2 here to cancel out that. And this is also an indefinite integral, so I'm going to put a plus c. What happens if we have the integral of seemingly nothing dx? Well, there can't be nothing there, so that would have been just a 1 sitting in there, and the antiderivative of 1 is x. This is an indefinite integral, so I'll need a plus c here. Let's go into the next one. It's also an indefinite integral. Let's take the antiderivative of this term first. That would be x cubed before we took the derivative, and I'm getting a 6 here, so that must have been a 2. Now the antiderivative of secant squared is tan x, and we need a plus c. Now we've got some definite integrals here. I want to take the antiderivative of x cubed. So that would be x to the power 4 over 4. And I need somewhere to put these upper and lower bounds here. So I use the evaluate at symbol, and it's a long vertical bar here. And I just rewrite my upper and lower here, which means that I'm going to evaluate this at 2 and then subtract this evaluated at negative 1. So first I put in the 2 and then minus negative 1. And then I just work that out. So 2 to the power of 4 is 16, divided by 4 is 4 again. And negative 1 to the power of 4 gives me positive 1. Just 4 minus a quarter. And then we'll rewrite this so we have a common denominator. 16 over 4 minus 1 over 4 is equal to 15 over 4. Next one, I'm going to rewrite this first of all into exponential form. So I have x to the power of negative, because I'm putting it up here in the numerator, negative 2 divided by 3. The index of my radical is the denominator of my exponent. Now I'm ready to take the antiderivative of this. So if I add 1 back to here, I would have had 1/3. Now I don't see any constants in front here, so if I multiply this down, I need to cancel it out, so I'll put a 3 here. I'll use my evaluate at symbol and put a negative 1 and 27. So first put in the 27, so 3 cubed root of 27 minus 3 cubed root of negative 1. Bringing it back here, we've got the cubed root of 27 is 3. 3 times 3 is 9. And the cubed root of negative 1 is just negative 1. So negative 3 times negative 1 is positive 3. So 9 plus 3 is 12. Now I have this ugly looking integral, and if you ever get something that you don't think you can find the antiderivative of, try to simplify it before you take the antiderivative. So in this case, I can divide every term by t, so t squared divided by t just leaves me with t. The square root of t divided by t leaves me with 1 over the square root of t, and 2 minus 2 divided by t. And this time, see, we're integrating with respect to t. And we can take the antiderivative of t, no problem, and 1 over the square root of t as well. And that would be a 2 coming down, or a 1/2 coming down, so I need a 2 here. And minus 2, and I know that if I just have a t alone here in the denominator, that came from the natural log of t. Now I need my evaluate at symbol with my upper and lower bound here, and I will put in 4 into every one of these terms. So 4 squared divided by 2 plus 2 root 4 minus 2 natural log of 4 minus, and I'll put some brackets here and distribute in that negative in the next step. So I'm putting 1 in each of these terms now, so 1 over 2 squared plus 2 square root of 1 minus 2 natural log of 1. This would be 16 divided by 2 is 8. This would be 2 times 2 is 4. We've got to leave this one like this. There's nothing we can do with that. We've got minus 1/2. And we've got a 2 here, and it's got a negative, so minus 2. And the natural log of 1 is 0. So I'll put a 0 here, just so you know where it went. But we're going to get rid of that in the next step. Okay. Now we can just add everything up here. So 12, 10 minus half is 9.5. So we could put 9.5, or if you didn't like decimals, you do, how about 19 divided by 2 minus 2 times the natural log of 4. And then you might just want to go a step further, but let me just remind you, this is perfectly mathematically correct. So is this. Just maybe you want to keep playing with this, you know. We've got the natural log of 2 squared, and then I can bring that down. So, you know what, this is 19 over 2 minus 4 natural log of 2 as well. You should be able to find the definite or indefinite integral. And remember your plus e for the indefinite integral. And look out for discontinuities in your interval of integration. There's some questions from the textbook. Give them a try, have some fun, and see if you know what you're doing.